Okay, welcome to our special session this morning. It's a fireside chat on a new collaboration to advance propulsion technologies. And as a longtime propulsion guy, this is going to be good. I'm Dan Dumbacher, the Executive Director of AIAA, and I have the honor of introducing the session. We're thrilled to have NASA Administrator Bill Nelson here with us to kick this fireside chat off. Senator Nelson was sworn in as the 14th NASA Administrator in May 2021. He brings a wealth of experience to this role. He chaired the Space and Science Subcommittee in the U.S. House of Representatives for 6 years, and in the U.S. Senate for 12 years. He served as the ranking member of the Senate Commerce, Science, and Transportation Committee. He was recognized as the leading space program advocate in Congress, working in a very bipartisan fashion to pass landmark NASA legislation in 2010 and 2017. I got to have some fun with that legislation. It was great. During his time in Congress, he was a strong advocate for NASA Earth science programs and a vocal proponent for STEM career training and education. In 1986, he flew on the 24th flight of the Space Shuttle, conducted 12 medical experiments while on board Columbia, including the first American stress test in space and a cancer research study. He has served in public office for more than 4 decades, and prior to that served on active duty in the U.S. Army. AIAA has been excited to see NASA benefit from Administrator Nelson's extensive background, bipartisan relationships, and fantastic leadership. We look forward to continuing to support Senator Nelson and the agency as they make critical advances in space exploration, technology development, and aeronautics research, and we're delighted to have him join us here today. Administrator Nelson will provide opening remarks, then our fireside chat will begin with Dr. Stephen Howe, NASA Deputy Administrator Pam Melroy, and DARPA Director Dr. Stefanie Tompkins. Please join me in welcoming Administrator Bill Nelson to the stage.
Hey, good morning, everybody. On behalf of Pam is our deputy. Pam is an astronaut commander, Pam Melroy. She also is an Air Force test pilot. on behalf of her and the entire NASA team, it's an honor to be here, and it's an honor to be at one of the largest platforms for technology and innovation. I also want to thank DARPA Director, Dr. Tompkins. Today is a major moment in the never-ending quest to expand humanity's reach. NASA has always dared and never stopped exploring the unknown and the unknown in air and in space. And in this era of exploration, we are creating sustainable and cutting-edge technology. And it is this technology that will take explorers further than ever before. 61 years ago, President Kennedy announced that we'd send a man to the moon. That was once a lofty vision, then it became a reality. And in the years to come, we are now going back to the moon and beyond. The Artemis generation will land the first woman and the first person of color on the moon. We will establish a long-term lunar presence in a hostile environment. We will use what we learn to take the next giant leap, and that is sending the first astronauts to Mars. It's another lofty vision, but it's one that is within our grasp. We need the technology that will take adventurers there faster and safely. It will take commercial, international, and governmental partnerships to reach the unreachable. So why are we here today? I'm pleased to announce that the nation's next big development in space technology is a major investment in getting to Mars. NASA will partner with our longtime partner, DARPA, to develop and demonstrate advanced nuclear thermal propulsion, a revolutionary technology that will allow the United States to expand the possibilities for future human spaceflight missions. Our goal is to launch and demonstrate a successful nuclear thermal engine as soon as 2027. The idea of nuclear thermal propulsion is not new to NASA or to many. A half-century ago, the United States conducted its last nuclear thermal engine test under NASA's Nuclear Engine for Rocket Vehicle Application and rover projects. Here's what we learned and we know to be true. Conventional chemical propulsion is not the most efficient way for our astronauts to do a deep space mission. Nuclear thermal propulsion is much more powerful, with 2 to 5 times the efficiency of chemical propulsion. And with the help of this propulsion system, astronauts will be able to journey to and from deep space faster than ever, a major capability to prepare for crewed missions to Mars. Deputy Administrator Pam Melroy has led NASA's strategy for sustained human presence in deep space. Our Moon to Mars objectives are guiding our work, and we are now beginning to outline the architecture for future exploration, not only with nuclear thermal, but also possibly with nuclear electric propulsion. Expanding our partnership with DARPA and its Draco program will help, and it will help us create a new era of space transportation. One small step is one giant leap for humankind. And this partnership will take us one step closer as we dare to explore the unknown. Let us dare to ignite the future farther, faster, together. Congratulations to both NASA and DARPA on this exciting investment in the future of human space exploration. And so I want to call up the panel that will be speaking on this and then have the discussion. You all come on up.
Good morning. I welcome you. I'm Steve Howe. I welcome you to the new collaboration to advance propulsion technology session. I was 25 years at the Los Alamos National Laboratory and 10 years as director of the Center for Space Nuclear Research at the Idaho National Laboratory, and currently working for my son at Howe Industries in Phoenix, Arizona, part-time. I just wanted to mention how I first got introduced to nuclear thermal rockets. In 1982, ex-senator and Apollo lunar astronaut Harrison Schmitt approached the director of the Los Alamos National Laboratory and instigated a joint study between NASA and Los Alamos over 6 months to identify all of the issues of a human mission to Mars, what it would take. And I was the co-chair of the Los Alamos team, and my specific task was to look at using an NTR, nuclear thermal rocket, and how it might benefit the mission to Mars at the time, and then to identify the issues necessary to recover the technology. So as Administrator Nelson mentioned, in 1957, Los Alamos was given the task of the rover program, which was to design a nuclear reactor with an appropriate fuel that could reach about 2,500 degrees Kelvin, and design the reactor part. In 1963, the Aerojet Westinghouse team was awarded the NERVA program, Nuclear Engine for Rocket Vehicle Application, to make that into an engine. So from 57 to 72, they tested 23 different reactor engine prototypes, all the way to TRL 6+. They even had a test stand with a reduced, steam-driven reduced atmosphere. The largest test during this program was the Phoebus 2A at 4.5 gigawatts, 250,000 pounds of thrust. The smallest engine was the Pee-wee, which was late in the program, at 500 megawatts and 25,000 pounds of thrust. Both of them had measured specific impulses of 850 seconds, which is almost twice that of the LOX hydrogen main engines on the shuttle. So the potential benefit was tremendous for a factor of 2 of ISP. The programs ended, both of them, in 1972 when the country decided to no longer travel to the moon. And it ended there. Several of us have tried over the years to revive and pursue the research and keep the technology alive, if you will. As we just heard from Administrator Nelson, the U.S. is now interested in expanding operations in cislunar space, going back to the moon, maybe going on to Mars. Over the last few decades, several National Research Council studies have done comparisons of propulsion systems and almost always concluded that the NTR was certainly mission enhancing and sometimes mission enabling for some of these missions based on survivability of the crew. So we're very honored today to make this announcement and have with us Deputy Administrator Melroy and Director of DARPA Stefanie Tompkins to talk about this collaboration that's going to happen. The format is going to be opening comments from Pam and Stefanie, then a series of prepared questions that we will have a discussion, and then we'll open it for question and answers from the audience. So with that, I'll turn it over to Pam, and I think the green button.
Thank you. We're incredibly excited to be here today. With this agreement, we're undertaking some really important work. As the nation's civil space agency engaged in peaceful exploration of space, we're always seeking opportunities to buy down risk and yet also advance the cutting edge of technology. So together, NASA and DARPA have worked on multiple projects to support our respective missions that neither one of us could do alone. We do hypersonics research together, and more recently, development of robotic, on-orbit satellite refueling and servicing. So today's announcement just continues to strengthen our partnership with the demonstration rocket for agile cislunar operations, or DRACO. It's got really big implications for NASA's Moon to Mars work. As the administrator referenced, we have a Moon to Mars strategy, and we have objectives that we've been working on now and in the coming years to achieve our big goal. So our intent is to lead and develop a blueprint for human exploration and sustained presence throughout the solar system. That is a very important goal, and we think that these advanced technologies will be a critical part of it. Within our objectives buckets, we have several buckets that include science, infrastructure, operations, and then, of course, transportation and habitation, because you got to get there and stay alive while you're doing it. And DRACO will be a critical part of evaluating the technologies that will take us deeper into the solar system. And by the way, Steve, there's no might. We're going to Mars. So we do know that we need to be evaluating options for power and propulsion. As Steve referenced, that is absolutely critical for us because of the risk to the crew. And I'll talk a little bit more about that. The key thing, of course, is, as both Steve and the administrator mentioned, nuclear thermal does have high thrust to weight similar to chemical, but it's 2 to 5 times as efficient. So these propulsive capabilities will enable the U.S. to enhance its interests in space and to expand the possibilities for the future, supporting NASA's long-duration human missions, but potentially also our scientific missions as well. So this is really a tangible step forward for us in getting humans to Mars and our deep space exploration. The key thing is that this will allow us to evaluate the opportunity to move faster. If we have swifter trips for humans, they are safer trips because of the incredibly harsh radiation environment that humans have to endure going all the way to Mars and in other deep space destinations. So the ability to go faster can make a huge difference for the safety of our crews. So as I mentioned, this also has the potential to extend into creative science missions that are not possible today. In the future, we really hope to have more scientists going to do studies in situ, and we need those scientists in residence, not just on the moon, but also Mars. So anything, of course, that we do like this also has an enormous impact on our aerospace base. It's got a big ripple effect in economics, commercial capabilities, jobs, and who knows what will come from this investment that we're doing together. So here at SciTech, I know you're going to be talking about a lot of really exciting things to push the boundaries of what we can do, all of which will also inspire students and early career people to join us in this amazing journey that we're going on together. And this agreement is certainly an inspiration to me, and I think to a lot of people. So I want to thank Stefanie and DARPA, and commend the hard work of both the Space Technology Mission Directorate at NASA and the DARPA teams that got us to where we are now. And I look forward to seeing the fruits of our collaboration and to our discussion this morning.
Thanks, Pam. Thank you, Pam. And thanks, Steve, for a really great introduction to a topic that may not be something that everyone in the audience lives and breathes every day. So it's always helpful to have someone set the stage really well. So I have to echo what Pam said. It's so exciting for us as part of DARPA to be here on the stage with NASA to talk about this endeavor that could change our transportation capabilities in cislunar and outer space. Pam listed some DARPA programs that have played a role in notable NASA achievements, and vice versa, in all honesty. We think nuclear thermal rocket technology, so NTR, has the potential to be one of the next ones on that great list. We're excited about the fact that it takes us back a little bit to our roots, particularly, a lot of our work in collaboration with NASA to develop a Saturn V rocket that took humans to the moon for the first time. It feels like a really great circle that we're going on with, ever-expanding directions in the solar system. Sorry, just trying to handle the technology. The classic DARPA joke. We invented the internet, but sometimes we can't make this line. So I expect everyone here knows NASA really well. You may not all be quite as familiar with DARPA, so let me just take a couple seconds to give you that background. First of all, we were born the same year as NASA, and both of us very much in response to the launch of the Sputnik satellite, which presented a pretty amazing technical achievement, but also a great surprise to the United States. So for the last 65 years-ish, DARPA has held steady to the mission that started way back at the beginning, which was to both prevent that type of technological surprise and to create it ourselves. And we typically do that by making pivotal investments in breakthrough technologies relative to national security. So our role is to take the technology excuse off the table for doing that next great leap ahead thing. So NTR technology then aligns with that mission, holds a lot of promise, as you've already heard multiple times, in terms of more efficient ways of traveling to Mars. And also for a lot of us, when we think about the future of space, just providing the maneuverability necessary to give space leadership options. So when you think about national security, maneuverability is actually one of the things that everybody operating in air, on land, on sea, undersea, really, really prizes. And it's a capability that we don't have enough of yet in the space environment, and it's one that we aim to be able to prove is at least possible to make that another option for commercial leadership and for basically the future of economics in space. For those of you familiar with the history of nuclear engine development, which is probably a much larger percentage of you than in the average audience, it's important to point out how our technology is actually new. So as Steve mentioned, a lot of really groundbreaking work in NTR technology has already been done. Hasn't been done in space. And one of the key enablers that lets us sort of go forward today, which might not have been possible even a few years ago, is the ability to use a different type of fuel. So rather than using highly enriched uranium, we're taking advantage of the ability of using high-assay, low-enriched uranium, or HALEU, which is part of this whole burgeoning economic explosion in nuclear energy, and particularly in small reactors. So it's an exciting opportunity space for us. That ripple effect, allowed obviously changes in space policy and lets us go forward with taking some risks that might not have been possible not too long ago. Or you've already heard enough, I think, about NTR propulsion and what it offers. The bottom line is that we are a spacefaring nation, and ever more and more part of a spacefaring planet. So operating in space is important to scientific discovery. It's ever increasingly more important to modern commerce, as well as to national security. To maintain our technological advantages in space, we think we require leap-ahead propulsion technology, and that's what this program aims to provide. One final thing, before we dive into the deeper conversation, I want to thank our partners in the U.S. Space Force. They've signaled their support for Draco with the intent to provide us launch support when it's time to do the demonstration. So we look forward to today's conversation and all of your questions. Thank you.
So I'm going to ask you to go into a bit more detail, and we'll start back off. Stephanie, we'll just let you continue a little bit more on this maneuverability. In other words, is this inclination changes, orbital changes, fast transits? I know you can't talk about missions very much, but
Well, it's very much all of the above. Okay. And I think one of the things I'd like to do, just to sort of capture people's imagination, is repeat some things that the Space Force, which is all of 3 years old now, I think, laid out when they were first kind of laying out this vision of what the Space Force's mission was. And one of the things that they said was, you know, as the U.S. Navy has really, really important missions in things like disaster relief, humanitarian assistance, and in protecting commercial shipping lanes, they said this is going to be an important part of their future as well. And, you know, in a world where the economics of space, and particularly some of the excitement about cislunar space, are continuing to grow, it's really important that this is a capability that is at least available to them. So all of the above in terms of the specific things, and that mission space, I think, really does span this classic breadth of commercial, civil, and national security missions.
Good. And Pam, in a similar vein, more detail on your, I know going to Mars is fast, you want to go fast, but what about just cargo transport to the moon? You get a factor of 2 with this ISP, right? So is there an application for some lunar missions that the NTR is applicable to?
I think there absolutely could be. You know, one thing that we have certainly learned from operating the International Space Station is humans and science take a lot of logistics. And so being able to get things back and forth is very important. In some cases, the slow boat from China is absolutely fine. I don't know if that's, you know, it's a saying anymore. It was when I was a kid. But, you know, the very slow, that can be very useful for certain mechanisms. But it isn't ideal, especially for humans or for high interest or, you know, high capacity cargo that we're trying to take care of. So we do think that there is the potential. We'd love to see commercial spin-offs come after a successful tech demo that may enhance our ability. But of course, a huge part of this is the blueprint for sustained human presence and exploration. We think those trades are also going to be out there between chemical, electric, nuclear electric, and nuclear thermal. We need to be doing these tech demonstrations now to prepare ourselves for an analysis of alternatives in the early 2030s for a Mars transport vehicle. So that's really what this is about.
Excellent. So I'm going to go off tab here a little bit in that we know the Russians put 30-some reactors up in space. They were small, 10 kilowatts. We had one reactor, the SNAP-10A, in '64, but the U.S. hasn't launched a reactor. We've launched RTGs and space batteries. Was there a problem in regulatory approval? Is this a big hurdle? Do you think this is, you guys have got a big burden here trying to get this launched. Pam, we'll let you start.
Yeah, I think probably the biggest hurdle for regulatory has actually been with commercial, and HALEU is absolutely going to help that. SPD 6, the Space Policy Directive 6 from the White House, provided a lot of clarity in this area. I think the government has always been capable of doing what it wanted to do, if to find the authorities to do it. But I think the clarity of the agreement between DARPA and DOE, where DARPA has the oversight authority, is absolutely going to make this move faster. So I think there's a lot of different pieces that came together in that policy environment. But for me, the really big outcome is using HALEU is going to streamline a lot of that because it's not considered weapons grade material. And so that means also the potential for commercial spin-off is there.
Excellent, very good. So safety. I mean, obviously the public's going to say, you're going to put a reactor over my head. You want to talk about, Stefanie, a little bit about the safety for launch operations and operations in space?
Absolutely. You know, I have a colleague who likes to refer to the times decades ago before safety was invented. I will tell you safety has been invented, and we're putting a lot of time thinking into that. Our amazing program manager for this project has been sort of living and breathing a lot of the safety considerations. So, you know, for example, The system is essentially going to be designed so that there is no way to actually get the engine going until we're fully on orbit. And we have a lot of safety measures built in for any kind of an accidental launch failure or things like that. It's just embedded in the entire culture. The rocket is designed to basically stay in space in an orbit that would not degrade until well past the lifetime of the actual fission materials. So it's just sort of embedded in the entire design process. So
good, excellent.
Very, very important.
Essentially no risk, no risk to the biosphere.
Yeah.
So along this, in the original days of rover NERVA, there was a joint program office between AEC and NASA, Atomic Energy Commission. And can you talk a little bit about how this is going to work, this collaboration? Pam, are you having a joint office? Are you sharing offices? How is NASA going to work with DARPA to do this?
Well, part of it is to, we've been focused on structuring with kind of clear lines of responsibility. NASA will be working on the engine itself, basically, the rocket engine and the reactor part, and that allows us to kind of make sure that we've got, I think this is really important whenever you set up a joint effort like this, who's doing what and who has responsibility for what. The good news is that we have been partnering with DARPA through the Draco program from the beginning at the program office level. So yes, we have a program office at NASA that is dedicated to all things nuclear, and they'll be working closely with the Draco program team. Do you have anything to add?
Yeah, I think that, often that structure evolves through the life of the program, and what you need sort of in the first phase when you're doing exploratory designs versus what you're doing when you're getting ready to launch will vary. I think the bottom line is we have really strong communication, people that respect and trust each other, and they will adapt as needed. And of course, there are other partners as well. So the Department of Energy, Pam mentioned that they have authorized DARPA to take responsibility for this overall project, and they will be acting in an advisory capacity when we need it, given all of their expertise in nuclear power and things like that. And of course, the Space Force will become a little bit more of a role as we get closer to actual launch. So
I'll just add to that, in my experience with joint offices, one of the things that's really critical to make it work is that you have the support all the way at the top of the agency and positive relationships. And we couldn't have a better relationship. Yeah. So that helps a lot when you have things you have to work through.
So it's not on the list, but I'm going to ask you anyway. Funding. Do you have congressional support for this? I'll let either one of you take it.
Yeah. Oh, absolutely.
Okay.
We have it built into our budget for the full duration of the project.
Excellent.
Obviously, we are counting on mission partners for certain parts as we go forward, but those commitments are very positive.
Certainly, we have in the 23 enacted $110 million in this area. And of course, we will continue to submit budget requests that will support this activity. One thing that's kind of nice is that everybody loves a joint project. Because, the sense of our congressional committees and even OMB examiners is that we're, getting more bang for the buck. So that is helpful.
So Pam, just a couple of minutes then, if you want to elaborate, what's the difference between a chemical engine and a nuclear engine, just at a high level? What's the fundamental?
Well, there's a couple of key things. So for nuclear thermal, you do have a hydrogen tank. For if you had a traditional rocket, you would have to have two tanks. You'd have to have a fuel and an oxidizer. So in this case, the hydrogen is actually pumped into the reactor with a turbo pump that looks actually pretty much like a traditional rocket turbo pump. And then it's heated up and it's ejected out of the nozzle. But the fact that you're not carrying two, both the fuel and the oxidizer certainly provides some efficiencies. You talked about ISP, some of those things that make it more efficient. So there's, potential for mass savings in the end. So it's just, like, as you pointed out, very, very high ISP.
Excellent. Okay, I think we will shift. If we don't have to say anything else specific, we'll shift to audience comments. We have one for Stefanie. Are you collaborating with private companies, or do you plan to do so on this?
Oh, absolutely. So again, for those that aren't familiar with DARPA, we don't have internal labs. We don't do our own work. We get the crazy idea, and then we convince other organizations to actually do that scientific technical work. So we're in the process of evaluating proposals right now, and in a couple of months you'll hear more specifically about who will actually be doing a lot of this, the next stage of DRACO work.
Okay, I think they want a little more elaboration on why HALU. So I know you both have mentioned it, why it's good, but let's dwell on it a little bit more. What was the problem with HEU?
Sure, and well, as Pam has mentioned, when you start to get into highly enriched uranium, you get into significantly more safety areas that you have to pay attention to. There are more regulatory issues. You're starting to move closer to weapons grade material, all kinds of reasons, both technical and sort of societal, that affect how flexibly we would be able to do a program like this. So the availability of the high assay low enriched uranium sort of changes the game. So we're talking about sort of 5 to 20% enrichment, whereas with highly enriched uranium, you could be talking up to 90%. So it's a significant difference in the space that we're working in. It's also, as I mentioned, I think DOE is really, really embedded in this. It is a significant part of the future of portable nuclear power, and so it is something that they are very focused on. We're focusing on it for space, but it is actually an enabler for nuclear power, ground-based, sea-based, wherever else you would potentially want to use it. In the lab.
Now, you're planning for a 2027 launch. Nice and ambitious, DARPA hard, kind of a mission.
DARPA scary.
Yeah. Do you want to talk a little bit about altitude? How high is it going to be? Is it going to impact space station? Do you have to kind of time it right? Anything like that as far as the first test? Pam, do you want to?
No, I think Stefanie mentioned that it's critically important for us to get to a high enough altitude that the material will no longer be radioactive by the time it re-enters.
Right.
And so that's critical for us. So that's sort of a minimum at the 700 kilometer threshold, and maybe up to as high as 2,000 kilometers, both of which are well above the International Space Station.
Okay.
So
there's no issue
300 years plus for re-entry. So.
And again, I'm going to go off target here. Any radioactivity coming out of the exhaust? Are we putting anything into orbit that could last a while? Either of you want to take it, or?
So, I think it's just worth reiterating that part, that obviously we are putting radioactive materials into space, but we have designed the entire process to be safe, right? So that part of the reason of doing it in space, in a lot of ways, it's safer than having to do it on Earth.
And what comes out of the rocket engine is gaseous hydrogen.
Right. Exactly.
So,
I just want to emphasize
that.
It's not
gaseous
radioactive.
hydrogen. Which you can find a lot of in space.
Okay, we have a question that I think you've both covered, but we'll hit it again. After DRACO is successful, what do you expect the role of NTRs to be in the space domain? I think you've both kind of covered this from your own respective issues, but let's ask it a little bit differently. What's after DRACO? What's after the first test? You pop the bubble, regulatory, you put a reactor up in space, first time in 60 years. That's the big step. What's next? What's the next step after that?
Well, I'll start, because the longer and more profound answer is going to come from NASA. Because DARPA's role, we have a very short attention span. If we are successful, once we have proven this is possible, we will move on to something else, right? This is sort of the nature of DARPA, is we rotate our people, we're having them bring in these crazy ideas, and then we're taking the risks to demonstrate that they're possible, and then we're moving on. So it is most likely that once we have, if we're successful and we have taken this technology excuse off the table, then the idea is to help transition that to other parts of the U.S. government. NASA already has a very clear plan, and as we said, we're talking to the Space Force so that they can add that to the options that they can explore for what comes next for them.
Okay.
Well, if I could riff for a minute on what makes NASA different than DARPA, I think it's one of the things that's really fun is that we both are, our mission is to explore the unknown in air and space. And to do that, we have different mission directorates that work on aeronautics technology, that work on space technology, so cutting edge development. But we also have operational missions, right? So both for science and for human spaceflight. And so we are both a tech developer and also the transition partner, like take that tech and go actually do something operational with it, which is really fun to partner with DARPA because we have that DNA in our Space Technology Mission Directorate that's about tech demo and tech development, but we also have an in-house built-in transition partner. Does it make it easier? I don't know, but it is different. I know that one of the hardest things at DARPA is once you've demonstrated it, really encouraging the use of it and operationally, finding that transition partner. So, from my standpoint, I just wanted to point out that that's one of the different things about the way NASA works. We do think that there is the potential for commercial spin-offs to be useful in cislunar. That is the scale of Draco. It's really designed for cislunar operations. We do think that if we're successful, we will have to take one more step to look at the scale that we will need for a Mars transport vehicle, which is going to require some scaling of the technology. Probably less risky step, but also critically important, again, to that analysis of alternatives in the early 2030s.
Excellent. So I'm going to combine the last two questions from the audience. They appear to be a little bit concerned of the joint effort and meeting the date. So are you have you developed new ways of working together? Because usually when you get more chiefs in the kitchen, things often delay a little bit. So have you come up with any kind of something on new structure or new program management, or how do you think this is all going to just blend together and meet that 27 date?
So, I think Pam mentioned this. One of the best things when you're creating a complex organization is to have very clear lines of responsibility. So, people might be concerned about a joint design approach. You're not, this is not a free-for-all, right? Everyone understands what components they're responsible for, and clean lines of communication matter. So this is actually not that new, I think, for either of our organizations, and it's something that I think we both have a lot of confidence in. So we haven't invented new program management structures. We're pretty confident that what we're working with will be.
And this is the DARPA program. Yeah. It is the Draco program, and so DARPA will take leadership in most of those key areas, especially the safety responsibilities. Not that we won't be supporting in every possible way, but I think we're all really clear on that.
Yeah. It's also worth mentioning our goals are not in conflict, right? We are very much looking for the same thing. And so that helps too. So I know people probably think of stories where you've had organizations that were trying to take advantage of some overlap in interest. We have very, very well aligned interests, and I think that's a huge accelerator for making this work.
Okay, we're going to have one more question, but I'll lead it a little bit. I have made the claim recently that you guys have accomplished more in the past 3 years than I saw in 40. We kept pushing the Sisyphean rock up the hill and never getting there. So how's the landscape changed that has enabled this to now start to be considered? So Pam, why don't you go first, and then we'll wrap up here.
Well, I mentioned SPD 6, which was very, very important in the last administration. I think technology capabilities, certainly the onset of HALU has made people say, hey, some of these key barriers we're knocking down. I think there's also sort of a cultural barrier that we have finally gotten to the point where we've overcome. As you look at the clean energy transition, people are more sophisticated and understand that nuclear power is one tool in the toolkit for us to be considering. And so I think it's kind of gained broader acceptance that nuclear power has a place here on Earth as a part of our energy portfolio. And that's actually important too, because there's perceptions here that also have impacted that. But I think a lot of different things have sort of come together at just the right time, which is fun.
Exactly. I couldn't have said it better. I mean, I can also throw in there that obviously, in almost any technology space, we have been being able to take advantage of the opportunities in computational improvements, in new materials, things like that have all kind of moved forward. But what Pam mentioned, some of these like barriers to entry that kind of sort of faded away kind of all at once, really opened up the door for being able to be able to take this risk and try something that, intellectually I think people were prepared for quite a while. But you need that perfect storm of everything aligned in order to really take off. So.
I might pick up on the one tidbit you touched on, and that is if you think about rover Nerva in the 60s, there wasn't much of a computer to be had. They did they went from concept to test in 18 months. Now they had Senator Clinton P. Anderson to help them, and they had a budget that was unimaginable. But now we've got so much computational modeling, and we can do so much pre-work before the testing that I think that's what makes this, that is a landscape change in a sense from the old days. I think that's exactly right. I would just like to entreat all of the young people in this audience and all of the people that have worked for years pushing nuclear thermal rockets. I think now's the time. Support this in any way we can, and I look forward to seeing this fly in 2027. That's going to be pretty exciting. With that, I'd like to thank Pam and Stefanie again for an excellent discussion, and wish you all a good day. Thank you.
Thank you.